Hello students, welcome to IMS Academy. In this session I am going to discuss about the semiconductor part 5. Already I completed 4 parts in semiconductors. The subject is EDC, you know. This is particularly for ECE students, understand now. But this my explanation will be useful for gate aspirants and also for the students who wants to appear for the any PSU. Understand my point now. In the last class I explained about the intrinsic semiconductor. In today's class I will do the mathematical analysis regarding the intrinsic semiconductor and also mass action law. One by one we can discuss. The first we can do the mass action law, then after we can do the current density, conductivity of intrinsic semiconductor. Understand? Before going to the subject, I want to give some information regarding the IMS Gate Academy. The students who are willing to take admission in IMS Gate Academy can make a call to these numbers. Numbers are given here now. Here given numbers. They can make a call to these numbers only now, below given here now. But if the students gets admission in a in IMS Gate Academy, what are the program futures we can discuss here now? More than 800 hours of live classes with live interactions possible here now. Experienced faculties are there now. For each and every branch there are number of experienced faculties. They are having more than 10 years experience. So easily you will get the good subject from the faculties now. And also the IMS Gate Academy provides theory book, exercise books. The exercise book contains more than 4,000 questions. I hope these are the questions are more only now for the students' preparation. To crack the gate, these exercise books are just enough only, I can say now. And also because, but in these exercise books you can find the level 1, level 2, level 3, problems. Level 1 contains only basic questions. Level 2 is up to the gate level. Still students wants to go to the depth of the subject, you think it's so, they need to do the level 3, understand now. Anyhow, in the exercise book you can find all 3 level questions. But you can practice those questions now. I said more than 4,000 questions. But not only these 4,000 questions, more than 4,000 questions. But IMS Gate Academy providing more than 34 years gate questions bank with video solutions. So from this gate question bank you will get the still more number of the questions for practice. You can practice this now. But if you are not getting solution for any questions, you will find video solution and also alternative solutions also given here now. So easily students can get good subject from these two, from exercise book and also from the gate question bank. 12 personalized one-to-one mentorship sessions possible here now. And more than 130 online tests with video solutions of the mock test and many more possible. So without delay, you try to take the admission in IMS Gate Academy. The students are willing to take the admissions, they can make a call to this number. Contact number is given here now. Understand now. Now we can go to subject. We can enter into the subject now. Yes, good evening, Madan. But in the intrinsic semiconductor part I explained in the last class, I said already. Now we can do the mass action law at first. Mass action law. I am repeating once again. At thermal equilibrium, the product of concentration of electrons and concentration of holes is equal to square of intrinsic concentration. Square of intrinsic concentration. Intrinsic concentration. This is the mass action law. What it explains, what is this statement meaning? A thermal equilibrium condition means when the temperature is maintained constant in a semiconducting material, the product of concentration of electrons means N, and concentration of the holes is nothing but the P is equal to square of the intrinsic concentration. I can write the formula like this: N into P equal to Ni square. This is nothing but the mass action law, where N equal to concentration of electrons and P equal to concentration of holes. Ni is nothing but intrinsic concentration. But we are going to get a doubt here now. So far we have not seen Ni symbol. Suddenly entered Ni. What is that Ni? Ni depends upon what factor? Where from we can get Ni? Those points you have to know clearly. Ni means, I said, intrinsic concentration, no doubt. But it is fixed value for any material, or due to change of material, the intrinsic concentration gets changed or not. That is more important. The intrinsic concentration depends upon the type of the material. Silicon can have Ni of some value. Germanium can have Ni of different value. Already in the previous class, I think in one table I gave it. There is Ni for the germanium, Ni for the what now? Silicon I gave it now. But the value of Ni also Ni depends upon the type of the material I said. And also one more point is very important. Ni also depends upon the temperature of the material also. The temperature of the material is maintained different, you think it's so. Ni value also changes only, we can say now. But anyhow, this mass action law is applicable at thermal equilibrium condition when temperature is constant. Sir, but how to get that Ni value? From the manual. In the manual it will be given the type of the material and temperature will be given. Corresponding to that, Ni value will be given now. So Ni is a 300 Kelvin is given, germanium it is given. From the table you can get, from the manual you can get intrinsic concentration. Anyhow, what you would understand, Ni depends upon the temperature and type of the material. That is more important. Understand now. And also, what is the application of this Ni? That is very important. Mass action law. What is the application of mass action law? That is more important now. Suppose in a material, in the semiconducting material, the impurity addition is made, but before that one more point also you must remember. This mass action law is applicable for the intrinsic semiconductor or even for the extrinsic semiconductor. 100% mass action law is applicable for intrinsic and extrinsic also. For both it is acceptable. Understand now. But suppose in the extrinsic semiconductor, whatever, suppose in a material you want to find the minority carriers, how many existing? If you want to find means, you should use mass action law only now. Minority carriers, how many exists in a given semiconductor? That you can determine by using the mass action law. I say, suppose you want to find the concentration of electrons in the given material. N is the minority carriers, P is the majority carriers. So, N equal to Ni square by majority carriers. You must take majority carriers. Majority carriers. This formula you can use directly. Majority carriers are nothing but the P only here now. Majority in the bracket I can give. Majority carriers is nothing but the P. But if you want to find out the minority carriers, the holes, the same way. Holes you want to find means P equal to, you must use Ni square by majority carriers. Now P is the minority carriers. majority carriers. You must use that now. Or directly formula you can take now, minority carriers equal to Ni square by majority carriers. That way you can find it now. That is mass action law. Now we can go for next one. The current density in, but I want to find the current density in intrinsic semiconductor. In the last class, I explained what is intrinsic semiconductor. In the intrinsic semiconductor, I want to explain current density in intrinsic semiconductor. But just I am repeating about the intrinsic semiconductor to certain extent, certain level, already explained. A pure type of semiconductor is called as an intrinsic semiconductor. In the last class I gave it. The first point. Second point is nothing but in the intrinsic semiconductor, the concentration of electrons and holes are equal. How electrons and holes are equal means I explained by using the energy band diagram. How many number of electrons are moving from valence band to conduction band, that many number of the holes are creating in the conduction band, valence band. I say I have taken the conduction band. I got here the 4 electrons, for example. I got 4 electrons here now. Finally, I am having 4 electrons now. If I have 4 electrons in the conduction band, that many number of holes will be created in the conduction band. These many number of holes will be created now. Understand my point now? But in the intrinsic semiconductor, one more point you need to understand. Sir, whenever I am applying energy to the intrinsic semiconductor, number of electrons are going to the conduction band, thereby occupying electrons. The holes are creating in the what now? Valence band. After some time, can you find this valence band, this is the conduction valence band, can you find valence band to be empty? Possible? All the electrons can reach to the conduction band or not due to application of the temperature for a long period of the time, because the application of the energy for a long time. No, it is impossible. Electrons are not going to be steady here now for a long time. For few seconds only they are going to stay in the conduction band. After some time, electrons is moving from here to here. After some time, the electrons will try to come back and fall in the what now? Hole. That means the recombination of the hole is possible. Initially, number of electrons are generated in the conduction band. Then after, the electrons will try to fall in the valence band and also recombine with the hole only now. At the time of recombination, what is going to happen? Some energy is going to release. When some amount of energy is released, that energy is just enough to break the what now? Bonds here now, to make the electrons to move from valence band to conduction band. So this process is going on continuously only now. Multiple number of electrons are generating, and also what now? Recombination is also done. This is a continuous process only now. So in this case, we cannot find valence band to be empty at any cost. That point is very important. But I would like to find the current density in the intrinsic semiconductor. But a total current density in total current density that is denoted by symbol J equal to current density here possible by electrons and holes also. In the conductors, we are finding current density due to electrons only. But in the semiconductors, you can find current density due to electrons, Jn, plus current density due to holes. Current density due to electrons, I gave you already. What I gave it already? N into Q into mu n into E is given here. Current density due to electrons is given like this. Current density due to holes, I can put P into Q into mu P into E. But the point what you have to remember, in the intrinsic semiconductor, concentration of electrons and concentration of holes are equal, I said already. What I said already? For intrinsic semiconductor, concentration of electrons equal to concentration of holes. N equal to P is possible. That is N equal to P equal to, I would like to take it as Ni is the symbol I have taken here now. N equal to P, that equal to Ni only mostly. It is equal. But in this case, if I substituted N equal to Ni, P equal to Ni, what is going to happen? You please watch. J equal to Ni into Q into mu n into E, I can note down here, plus the P is nothing but Ni again into Q into mu P into E, I can put here now. But certain terms we can take common. What those terms, what those are taken common? J equal to Ni is taken common, Q is taken common, E is taken common. I will get finally mu n plus mu P, I can get here now. This is total current density in intrinsic semiconductor. Units are amperes per cm square is possible, or amperes per meter square also you can put it. That is possible. This is current density formula for intrinsic semiconductor. What about conductivity in intrinsic semiconductor? That also we can discuss. Conductivity. Conductivity in intrinsic semiconductor. Intrinsic semiconductor. But I wish to find the conductivity. But the same way, just like a current density in semiconductor, conductivity in semiconductor is equal to conductivity due to electrons plus conductivity due to holes. Addition of these two will give total conductivity. I say total conductivity that is given a symbol sigma, that equal to conductivity due to electrons plus conductivity due to holes. I can put here now. Conductivity due to electrons I gave already. What I gave it? N into Q into mu n already given. N into Q can also be called as a charge density, I said in the last class. Charge density into mobility is nothing but conductivity, we know very well. In the same way, conductivity due to holes means charge density of holes, P into Q into mobility, product of these required. But you know very well, for intrinsic semiconductor, for intrinsic semiconductor, N equal to P equal to Ni is the symbol is taken, already given. that Ni value I would like to substitute here now. Then sigma equal to, I can write N is nothing but the Ni into Q into mu N plus P means Ni into Q into, sorry, this is a mu P. This is a mu P required. P into Q into mu P I can write here now. But I can take Ni and Q common. The finally conductivity I can get Ni into Q. If it is taken common, I am getting mu N plus mu P. So you can use this formula to find out the conductivity. But that way we can find the conductivity here now, understand. But you will get units of mho per centimeter. Conductivity in mho per centimeter is possible. Mho per centimeter. Understand now. The next one, conductivity also completed. What about the resistivity? Resistivity means you know very well. Resistivity in intrinsic semiconductor. Resistivity in intrinsic semiconductor. In intrinsic semiconductor. But the resistivity in intrinsic semiconductor is denoted by symbol rho. Denoted by symbol rho. Rho equal to what I can say here now, reciprocal of conductivity is said to be resistivity only now. Reciprocal of conductivity, rho equal to 1 by sigma. Sigma means intrinsic only now, sigma I. Sigma you got Ni into Q, rho equal to 1 by Ni into Q, Ni into Q, mu N plus mu P we can take, mu N plus mu P. Yes, this is the formula we should apply to find out the resistivity. Units of resistivity, ohm centimeter. I can put ohm centimeters. So like that. But these are the formulas are mostly useful in doing the problems only now. Understand now. Now one question based upon the semiconductor I will give. You try to do that one. Understand. I will give one question. Find concentration of electrons, concentration of electrons, and concentration of holes, and concentration of holes, at minimum conductivity, minimum conductivity. I am giving now. Find the concentration of electrons and concentration of holes at minimum conductivity. Minimum conductivity or maximum conductivity, it doesn't matter now. Maximum or minimum. According to maximum, minimum, you know, derivative of something equal to 0 we are going to use. What is the meaning of that? You can understand. I will give clearly. Suppose here I gave, but I want concentration of electrons. This is the question I gave it, solution. But I want concentration of electrons, N value required, and also concentration of the holes are required at minimum conductivity. Minimum conductivity in semiconductor. That is very important. Semiconductor. I didn't specify whether it is an intrinsic or extrinsic. Only in the semiconductor only I asked. Only in the semiconductors means you know The conductivity in a semiconductor is nothing but conductivity due to electrons plus conductivity due to holes. We know very well. So, at minimum conductivity, sigma minimum only this one. Sigma n is nothing but n into q into mu n. Sigma p is nothing but p into q into mu p, you know very well. But I don't substitute here now. The n equal to p star, p equal to ni star, it is not acceptable. That is applicable only for intrinsic semiconductor. In this question, it is not specified. Is it intrinsic or extrinsic? Not specified. If it is not specified, general formula you must take. General formula means nq mu n plus pq mu p only now. But here what I wish to say, in order to find the concentration of electrons, the P is to be gained with concentration of the holes only now. Concentration of the electrons only. P in terms of n you have to convert. If you want to find the P, n you convert in terms of the P only now. What I wish to say, just now I have done mass action law. By using the mass action law, the P you convert in terms of n from the mass action law. From the mass action law. The P equal to, you know very well, Ni square by P, Ni square by N. Ni square by N we can put now. Ni square by N, clearly I will write. Ni square by N I can write here now. But that I want to substitute here now. Sigma equal to, I will write. Sigma equal to, we know, n into q into mu n. Initially, I want to find concentration of electron. P is nothing but Ni square by N. Just now, I got Ni square by N into q into mu p. But at minimum conductivity, I want concentration of electrons. According to the maximum minimum, derivative of this sigma with respect to n is equal to 0 only. That means d n by d sigma by dn you find. Differentiate on both sides best. Differentiate on both sides with respect to n. Differentiate on both sides. Both sides with respect to n. Sir, why you are applying differentiation? With the differentiation, I can equate it to 0 as per the maximum and minimum. Differentiation is a must, understand. So, I want to differentiate d sigma by dn. I want to calculate. With respect to n means n derivative 1, q into mu n I can get. Here 1 by n differentiation minus of 1 by n square into ni square into q into mu p I can get here. Into mu p is possible. But my aim is to find n. This n value is required, you know very well. Sorry, not ni square here now. Yes, ni square by n, correct. Ni square by n we are getting here now. Understand now. Then I can write here now dq, this is equal to what? 0 only possible now. Now I want to take q, I can cancel here now q and q I can cancel. Q and q totally I can cancel. And still what is left? Mu n equal to, I can write ni square by mu p by n square I got. I want to find what is n. N square equal to ni square into mu p by mu n only. My aim is to find concentration of electrons. N equal to, I can write n equal to ni into under root of mu p by mu n. mu p by mu n. This is the formula you must apply to find out the concentration of electrons when there is minimum conductivity in a semiconductor. But now in the same way we need to calculate concentration of holes also. How we can find the concentration of the holes? I will explain now. You can do easily now, but I will do again. But we know very well total conductivity, we got it n into q into mu n plus p into q into mu p. Like that I formed. Here I can say, according to the mass action law, n I want to convert in terms of the p, ni square by p, sigma equal to, n is nothing but ni square by p into q into mu n. That equal to p into q into mu p is possible. pq into mu p is possible. But you can apply differentiation according to the maximum and minimum. Derivative of this function equal to 0. Differentiate with respect to p, I say. With respect to p, I want to differentiate. So d sigma by dp equal to 1 by p differentiation minus 1 by p square into ni square into q into mu n I can get. The derivative of the p is nothing but the 1 into q into mu p I can get here now. This is equal to 0 according to maximum minimum. I can cancel on both sides this q term. If I cancel, what is still left? Mu p equal to, I am getting here, mu p equal to ni square into mu n by p square I can get now. My aim is to find out the p, concentration of holes required. So p square equal to, we are getting here now, ni square into mu n by mu p. And finally, concentration of the holes equal to ni into under root of mu n by mu p. Yes, this formula is more important. The formula is very, very important. That formula. Concentration of electrons and concentration of the holes are required means this process we need to apply. In case you are asked to find out the minimum conductivity, how we can find minimum conductivity in the semiconductor? In case you want to find the minimum conductivity, what you have to do? What you have to do is, suppose you want to find minimum conductivity, you think it's so. If you want to find the minimum conductivity, already I gave it n into q into mu n, p into q into mu p also I gave it. Suppose in a problem you are asked to find out the minimum conductivity, but already you are getting the concentration of the electrons at minimum conductivity. You substitute n equal to what I gave it, n into under root of ni into, I gave it already. I gave already for n concentration of electrons equal to, I gave it ni into under root of mu p by mu n I gave it. Mu p by mu n I gave. Please check it if you want, you will understand. Concentration of electrons equal to ni into mu p under root of mu p by mu n. Under root of mu p by mu n. This q into mu n is taken as it is. Plus concentration of holes I gave already, ni into under root of mu n by mu p I gave already. If you want, you can check. Already done. P equal to ni into root of mu n by mu p into q into mu p. Q into mu p is allowed. Allowed this. There we can take what now, here the root times mu n is cancelled here now. The minimum conductivity I can get formula like this. ni into under root of mu p mu n, here it comes. mu p into mu n into q outside. But the root times this mu p will be cancelled here now. So I can write Ni into under root of mu p into mu n into q I can write. Thereby taken common certain times. What those terms are taken common here now? At minimum conductivity, Ni is taken common. Ni is to be taken common. Can you take Ni common? Sorry, all are equal only now. 2 times it comes exactly. 2 into Ni into q into under root of mu p into mu n. Yes, the formula we should apply to find out the minimum conductivity. Ni into root of mu p mu n into q, yes, that way we can calculate. So at minimum conductivity, what I did, how to find out the concentration of electrons, how to find out the concentration of holes, and how to find out the total conductivity, minimum conductivity. These are the points are more important. Yes, now we can enter into the extrinsic semiconductor, next level. Extrinsic semiconductor. Extrinsic semiconductor. Extrinsic semiconductor. But the pure type of semiconductor is said to be intrinsic semiconductor. I explained before. What about the extrinsic semiconductor? When impurity is doped with intrinsic semiconductor, then extrinsic semiconductor is formed. Doped means just addition only. But you should not say when impurity is added with, the word is not allowed. Here the technical word is doped is more important. Understand now. When intrinsic semiconductor is doped with what? Some impurity is doped, then forming extrinsic semiconductor. Impurity means there are 2 types of impurity elements here now. One is said to be pentavalent atom, second one is nothing but the trivalent atom only now. Based upon the addition of the type of the impurity, the extrinsic semiconductors are classified into 2 types again. One is a N-type extrinsic semiconductor, second one is nothing but the P-type extrinsic semiconductor. Why we should do the doping? The doping is not done, what's going to happen in the semiconducting material. The doping is not done, it is a pure type of semiconductor or intrinsic semiconductor. But we know very well, in the last class I explained, in the intrinsic semiconductor the conductivity is less. Conductivity will not be possible more. If you want to increase the conductivity of the mode, you should apply, you should dope impurity along with the intrinsic semiconductor. But the impurity means we are not going to add more. Very small concentration of impurity is doped. But it is a one impurity atom means one impurity atom is doped with millions of the what? Intrinsic semiconductor atoms only now. Millions of intrinsic semiconductors atoms are doped with one atom only now. At the time, what is going to happen now? But because of the addition, because of addition or because of adding, because of what now? Because of what now? Combining this impurity, can you find any change of structure in the material? I am asking you a question. Any student can give. Doping is nothing but the added one now. Technical word is nothing but the doping. What now? Doping we are using. That is nothing but the adding only now. But addition is made means, now you tell me, the structure of the semiconducting material is changing or not changing. I said in the last class, the semiconductor can have the diamond structure. There is a tetrahedron structure they can have now. But even you are adding the foreign material means impurity atoms. the structure of the material is going to remain same diamond structure or same tetrahedron structure only now. The reason is what? We are not adding the more concentration, very less concentration of impurities doped. That is why here we cannot find the structure variation, but wide range of conductivity will be increasing only, we can say. That's why for the sake of increasing the conductivity, we should use this impurity only now. But what I said, when intrinsic semiconductor when intrinsic semiconductor is doped with impurity, what is that impurity means? I will give now. I explained just now. Impurity. Then extrinsic semiconductor is formed. Extrinsic semiconductor. SC I will put now. Semiconductor is formed. Like that it is forming. Understand? Otherwise you can write intrinsic semiconductor plus impurity is nothing but extrinsic semiconductor. But how many types of extrinsic semiconductors are there? Two types. There are two types of extrinsic semiconductor. ESC, extrinsic semiconductor. I have written ESC. There are two types of extrinsic semiconductor. One is said to be N-type extrinsic semiconductor, negative type extrinsic semiconductor. The second one is nothing but the P-type extrinsic semiconductor, positive P-type extrinsic semiconductor. But when N-type, first initially we can take N-type extrinsic semiconductor. N-type extrinsic semiconductor, initially I want to explain. When this semiconductor is formed, suppose I have taken intrinsic semiconductor that is doped with pentavalent atoms. Pentavalent atoms, then forming N-type extrinsic semiconductor. N-type extrinsic semiconductor is formed. What we can say, what is that pentavalent atom? Atom which contains 5 valence electrons is said to be pentavalent atom. Atom which contains 5 valence electrons means antimony, I can put SB. One example I am giving now. But how that structure is to be drawn? How the bond structure is to be drawn? How the structure will be there with bond? I will give you. But how that structure means, according to the bond theory, I can draw like this. There is an antimony, SB. You know very well, antimony contains 5 valence electrons. This is germanium or silicon. Anyone you can take this side. The antimony is getting contact with germanium here. The bond structure will be like this only now. It goes still like this. Germanium. The structure is going on like this. This side and that side and this side and that side. How many number of valence electrons in the antimony means everybody knows. 5 valence electrons because it is a pentavalent. 5 valence, 5 electrons it can have. Germanium is a fourth group element. The germanium is a fourth group element. It can have 4 valence electrons. I can put 4 valence electrons this way. 4 valence electrons. In the last class, I explained when sharing of any 2 electrons are taken place, thereby forming a bond, that bond is said to be covalent bond, I said now. Here this electron and this electron is going to be shared at the time, thereby forming one bond. One covalent bond is formed. One covalent bond. The second covalent bond. Because the sharing of these 2 electrons, third covalent bond is formed. Even here the sharing of 2 electrons are done, so fourth covalent bond is formed. Finally, how many number of the covalent bonds are formed in this bond structure? The 4 covalent bonds are possible. That's why I can write number of covalent bonds. Formed is 4 in this structure, in the simple structure. Number of covalent bonds formed is 4 with an excess electron. This electron doesn't have one more electron to form the bond. It doesn't have. At the time, it is going to remain as an excess electron. I can say this electron is an excess electron. Excess electron, I can say. This is going to remain as an excess electron. That's you can write number of covalent bonds formed is 4 with an excess electron. Excess electron. But you try to catch the point. Antimony atom here, then number of bonds are formed here now, 1 excess electron formed. Like that, number of antimony atoms we are going to dope. There may be less only, but number of excess electrons are going to be created only now. The excess electrons are in the free space. They are going to move freely. Even the less potential is given, immediately they are going to move to the valence band. Immediately they are reaching to the conduction band only now. Easily they can reach to the conduction band. When you applied any external supply, then the flow of these free electrons are going to take place. At the time, conduction is possible in the extrinsic semiconductor. The conductivity we are getting in the intrinsic semiconductor is always less as compared to the extrinsic semiconductor with the same potentials only now. Understand now. Anyhow, in the extrinsic semiconductor, more conductivity is possible only, we can say. This is the information regarding the extrinsic for today class. In the next class, I will do the still more information regarding the extrinsic semiconductor. Before that, before completing the session, the students who wants, once again I am repeating here now, students who wants to take the admission in IMS Gate Academy, they can make a call to these numbers. Once the students gets admission in IMS Gate Academy, they are going to get the program features of these. More than 800 hours of live classes with live interaction possible. The theory, but the IMS Gate Academy provides theory book, exercise books. The exercise book contains more than 4,000 questions. 34 plus year gate questions bank with video solutions possible. 12 personalized one-to-one mentorship sessions, more than 130 online tests with video solutions of mock tests, and many more. The students wants to get the admission, they can make a call to these numbers and stand up. Don't delay. Try to join as fast as possible. There are number of expert faculties in IMS GATE Academy. They are going to satisfy with good subject, no doubt, understand. So far you enjoyed a lot with the subject, I hope now. Understand now. You share this link to your friends, and they will also get the information of the more only you can see. Understand now. You subscribe to this channel also now. Understand, don't forget. Understand now. Thank you all.